Hello, my name is Dr. Nicole Simon. This is Set Stale with STEM Online. I'm from the Engineering Physics Technology Department at Nassau Community College, and this is the online teaching conference, Sail into Online Student Success. Are you still teaching science the old way? Try teaching science online. Using simulations and virtual experiments, students can repeat laboratory experiments and increase retention of information. How can simulations and virtual experiments lead to better learning experiences? Well, this session will be presented by an educational technologist who's both a science educator and teaches science lab courses online. I'd like to talk to you a little bit about virtual learning environments. Virtual laboratory experiments are a way to provide remote access to equipment or software as a way to conduct experimentation without the physical equipment and the proximity of students. It's a virtual environment for simulation laboratory experiments that's domain dependent or object dependent, meaning that students are going to be using more simulated type of lab work that are using project-based learning, more inquiry-based learning, and it provides a learning opportunity that students don't necessarily have based on physical equipment, whether it's cost or safety. Some examples of virtual laboratory experiments. They allow you to simulate or replicate what's already in a laboratory setting. And as you can see on the screen, not only do you have your simulation area, but you have all the same variables you would normally have in a lab group, if not more. You can certainly still take your data and you have access to all of your graphical analysis as well. This is based on simulation. Quick definition of a simulation: an imitation of a real-world process that is demonstrative of gaining credence by drawing inferences from a real system. So you're not actually simulating in the aspect that you are creating something that's non-existent. You're creating something that certainly exists, whether it be in a lab or a field type setting, and you're creating a learning environment by drawing inferences from what actually exists out in nature. So it's a more realistic, real-world example of scientific learning. Again, another example, certain things you cannot necessarily duplicate in a lab situation, or some things you may not be able to replicate where students can repeat it. So for repeatability factor, you can actually take different species, or in this case critters. You can vary different variables where you have humidity, terrain, light, temperature, and moisture. And you can replicate it and see a side-by-side example of your control versus your experimental. Same thing that you would normally have in a lab. Again, it's just that repeatability factor for students. This is a wonderful demonstration that I typically use with my students for Doppler effect. Doppler effect happens to be a scientific phenomenon that is not easily replicated in a laboratory situation. I can't certainly get a jet out there for my students to play around with where you're hearing an overhead of a jet going by. Well, actually I can. We're right in the middle of a runway, but normally, class settings, you wouldn't be able to get a flyby scenario, nor would you want to put a situation where a student's out in a parking lot trying to drive by honking a horn to replicate Doppler effect. But being able to replicate it on a screen and have that repeatability where students can explore and analyze the information gives them a more exciting way to learn, where they're able to change different variables that are not feasible in a real-life situation. Another one, it's a wonderful opportunity to use the online labs because, again, that safety factor, and you also have a cost factor, is PhET, Physics Education Technology. It's at a University of Colorado. And this happens to be a wonderful example where it's something called the skate park, where students can design their own amusement park setting, and they can change the variables for kinetic, potential, and thermal energy. They actually get to create their own scenario. So not only are they replicating what they have in lab, they can take it one step further, where you're using critical thinking and you're thinking outside the box as far as creating your own lab type of situation. The use of computer simulations. It's generally accepted there are presently 3 educational uses for information technology in education: learning from computers or about computers, computers and learning with computers, and simulations fall into the last category, become one example of what Jansen's terms mind tools. Mind tools are actually a computer application that are used for, quote, engaging and enhancing multiple forms of thinking in learners. These, quote, mind tools require students to think deeply about the content they are learning, so they're critical thinking devices. Simulations, by processing this data in a short period of time, allow students to model the process of developing hypotheses, changing variables, and observing the results. Accumulating data, researching the values of a variable, then running the simulation to test these hypotheses. The entire process can be repeated until the learner demonstrates a clear understanding of the various elements of the environment. As critical thinking devices, they are intended to engage and facilitate cognitive processes and in the process develop critical thinking skills. This creates something called an intellectual partnership that involves using the simulations. Learners has to recognize the content while the computer performs calculations, stores, and retrieves the information. Not unlike what you would typically do in a physical laboratory situation, where a student would have to recognize the content, perform the calculation, and then retrieve that data and analyze it. The only difference is that this is going on simultaneously. Rather than having a student look at the equipment, read the procedure, sometimes bumble through the actual experiment, and then try to garner information and data out of that for an analysis, you're able to collect simultaneously while you're doing the experiment. And more importantly, not only are you collecting it simultaneously, you're able to change different variables along the way. So you can repeat the lab as you're performing it. The University of Oregon webpage on critical thinking consists of a more holistic definition of critical thinking. They say that it is not enough to be able to apply problem-solving strategies to a particular problem. However complex it may be, a truly critical thinker must be able to choose appropriate strategies and even create new ones when necessary. Well, in scientific situations, you're dealing more with a broad-based learning where you're trying to replicate what's already out there. Using simulations and online labs, you're not replicating what's necessarily done in a typical science situation. You're taking theoretical information, you're taking facts, and you're putting it through real-life practice. We're able to replicate situations and scenarios that are normally not found in a laboratory situation. Students can create their own lab experiments where they don't necessarily have that opportunity in a course. Students are able to recreate a lab if need be for more of a tutorial based, and certainly students are able to create their own experiment and alter those variables to take it to a higher level than we would normally actually ask them to in a lab setting. When attempting to develop a model of higher order thinking skills, most researchers present long lists of sub-skills considered to be part of the overall skills of higher order thinking, and then try to define these sub-skills. By letting the student define their own learning situation, they're thinking in a critical situation. That's the whole concept of scientific learning, to think critically and to learn to analyze. So rather than define what these goals and outcomes are, students perform in the labs, we can actually have them define it themselves as they move throughout the lab itself. Computer simulations and virtual laboratory science experiments. They do several things to help us out in the lab. Not just that they're computer-based and not that they're necessarily non-physical based, but they offer learners a more inquiry-based approach to scientific education. Again, most of the labs that you see that are physical labs are can-based. You're reproving something. Students know what gravity is. To reprove it isn't helping them learn something they've already memorized. Because they're less constructive learning experiences, students know what the outcome should be on a canned lab that you physically do in a classroom setting. By allowing them to create their own scenarios and play within a laboratory situation online or through a computer simulation, students are not using prescribed experimental outcomes. They're able to explore, and that's truly an opportunity that we'd love to see more in science education. Traditional experiments require learners to conduct experiments with known scientific outcomes. Again, it's that known scientific outcome that disallows them from exploring. Computer simulations and virtual laboratory science experiments have radically changed science and education. These laboratory experiments offer learners a more inquiry-based approach to science education, again, following that less constructed learning experience, and more importantly, do not provide the prescribed outcomes of traditional science classes. As per the National Science Education Standards Benchmark for Scientific Literacy in 2006, they state that the importance of inquiry-based science education throughout the United States is vital to progressive education, underscoring standards that address students devising scientific investigations incorporating higher order learning and promoting self-directed technology-centered learning. So you're incorporating everything that's necessary, that's not only from the National Science Teachers Association, but also National Science Education Standards. It's inquiry. It's using technology. It's thinking more critically. It's analyzing things in a non-prescribed manner. Most importantly, I'd like to outline that traditional courses use expository or teacher-centered labs. Computer simulations are not teacher-centered. They're solely learner-centered. Let's talk a little bit about critical thinking skills. How do we actually define them? Why do we use them? And why are they so important to science education? Incorporating critical thinking skills in science hands-on learning activities, instead of having students sit at their seats only hearing or reading about a topic, not only bring them into a lab, but put concepts into their head. They no longer use rote-based laboratory experiments and espouses both expository and kinesthetic methodologies that are hands-on. This has proven valuable to getting students to understand and relate concepts. Through PBL activities or problem-based learning activities, students can utilize a scientific method to test hypotheses, formulate procedures for testing their theories, and work to find solutions to scientific problems that are based on reasoning and logic. Do virtual labs meet these same objectives as critical thinking? Well, they allow you familiarity with the equipment. So some of the pros are that some curriculum incorporate operating instructions for lab equipments, similar to what students would see in a lab manual. Students can practice using equipment in a virtual realm before wasting resources with operational mistakes. But again, there are some cons. No substitutes for hand-on practice with complicated apparatus. But if you use students that are going into today's science fields, most of them are technology-based. So to teach them the old school method where you need more hands-on practice, if they go into the work field, they're not always in a hands-on practical situations. They still need to know the technology. And by having them replicate and having that repeatability factor in virtual labs, they're better able to understand where science is heading. I'm not saying that they shouldn't learn where science has been, but they certainly do need to know where it's going. Practice with concepts taught in lecture. Well, again, some of the pros of virtual labs meeting these objectives. The virtual lab curricula can be designed to meet the needs of a class, and students can repeat these virtual experiments for practice or developing conceptual understanding. So you can either use it as a tool for retention and remediation, or you can use it in lieu of a physical laboratory itself. A lot of times, most faculty will combine the two methods, where you'll use as a demonstration to show them what the topic is, introduce the material so they can actually perform the physical experiment, or some of them will actually use it in lieu of physical experimentations. And again, a con, doing or repeating lab exercises outside instructional supervision can be frustrating for students who lack conceptual understanding. So I think it's important to introduce the topic, show maybe a demo using a virtual lab so they grasp the conceptual understanding of that topic. And then if they do the physical lab, or if they do a longer virtual lab themselves, at least they've seen them. So I personally use virtual labs and virtual demos, so they get to see both of them. It's no different than if you used a demo in class and then used the physical lab. So whether your demo is online or physical equipment, you're still showing them that conceptual understanding and getting them to understand the material. Do virtual labs meet the objectives of applying the scientific method? The fundamental tenet of all science education classes is understanding the scientific method. Not all virtual exercises are models or demonstrations, and that seems to be a misconception, that these are very quick demonstrations of a physical setting. They're not. Some of the best virtual exercises out there will not only duplicate what I can do in lab, but will actually take my students longer, because once they get excited about learning, once they understand that conceptual material, they take it to the next level. They use that critical thinking, and they think on a higher level where they design their own experiment and they start playing, and playing is very good in a science education class or any education class, but they start playing with the equipment and start playing with the tools and try to see how much more can I understand. Whether they realize it or not, that play mentality is getting them to learn in a more critical applied situation. Unfortunately, not all virtual curricula allow students to develop the experiment using the scientific method. And that's a very big factor that you need to watch when choosing virtual labs or simulations, making sure it does apply everything that you would normally do in a typical classroom setting. I found many useful sources out there, and unfortunately I found a lot that are not as useful. But again, keeping in mind the goals and objectives of your actual physical lab is crucial. Do the virtual labs meet the objectives of developing online critical thinking skills? Well, you're developing the same critical thinking skills whether you're online or whether you're in the classroom. But virtual exercises allow students to make mistakes. And again, it's vital to learning. They need to make the same errors that they would do in a physical lab for an error analysis. They carry out experiments and, quote, process their time, giving instant feedback. which in some cases is a lot more useful than waiting a week later until you get a graded lab back to find out, oh, I didn't understand that concept. That instantaneous feedback allows you to correct your thinking and then again remediate it. There's also opportunities for self-analysis and reflection in the laboratory. You don't necessarily get that in a physical experiment. Yes, you do have an error analysis, and sometimes you have a reflection component. But to be able to understand that as you're going through and not at the end of the lab, again, is crucial. But not all virtual curriculum allows student feedback to their critical thinking to improve or reflect on the exercise. That's the same is true as if you do an on-campus lab. Not having that feedback to improve their critical thinking is not helping them learn. They don't just need to remember and memorize. That's rote memorization. That's a very surface level learning. To get deeper appreciation, students need to apply what they've learned to a situation. And if it's a prescribed outcome, they're taking what they've memorized and applying it to what they already know. By giving them a situation that they have self-analysis and reflection in a virtual situation, they're taking what they know and applying it to the unknown, and that unknown, again, allows them to think in a more critical manner. What limits the lab experience? Unfortunately, time, money, equipment availability, instructor time, resources, and knowledge, safety concerns, and student availability. Virtual laboratory exercises can remedy nearly all of these concerns. Usually there's a one-time fee where you buy the software or have the software written for you. It's a little bit more costly, but certainly you'll have it for a longer period of time. The amount of time it takes, again, it's no different than a physical lab. You need to allot that into your course. Equipment availability, as long as you have access to the software online, you certainly have that availability. Instructor time, resources, and knowledge. Well, in a lot of cases, there are tutorials that you don't necessarily have in a physical lab. From a personal experience, I have 30 students in a lab, and I'm split between several lab groups, and as one student calls me, I'm running back to the next one. Here, I can actually have my students in lab groups and either do it synchronously, where we all meet at a common time, and if they have questions, they're working together, and they can always ask me in a separate chat room, or they can work asynchronously, where they can work on their own time. And by allowing them more time, you have that student availability factor in, where students can actually work on their material, come back should they need, and they no longer have to worry that they would in a normal class setting, oh, do I have enough time to fix this? There's also a lot less safety concerns. Best practices combine learning modules. Virtual labs, unfortunately, are no substitute for hands-on, but they do integrate curricula and provide the greatest variety of learning experiences. So again, if you use both methods, you certainly would have more of a real-world holistic learning experience. The integrated curricula address a greater variety of learning objectives. You can only fit so much into a piece of equipment. But again, once you take that prescribed outcome out, students are able to create their own scenarios for learning, and they're better able to vary their learning objectives because they're taking it to a more critical thinking approach above and beyond what's expected in that typical lab. They prepare students for the use of virtual, real integrated systems in their future careers. In conclusion, non-traditional technology-based exercises enrich the laboratory learning experiences and increase student interest and satisfaction. Virtual laboratory experiences reinforce critical thinking skills and understanding of the scientific method. Selecting a virtual curriculum. We developed a set of standards of criteria that we use at Nassau Community College for virtual curriculum. There's emphasis on content, otherwise unavailable. And I think that's crucial because if I'm giving students the same information that they had or that they could have in a physical situation, all I'm doing is changing my modality. I'm not changing my thinking. It requires manipulation rather than simulation. Having students point and click is not helping them learn. Having them actually alter and manipulate and modularize the equipment really takes it to the next level because they're creating the same type of environment they would in a physical experiment. They need to develop critical thinking skills rather than just observational skills. Again, by choosing different curriculum and using different virtual software, you're not just observing, point, click, gather data, and the software does the graph. They need to think critically about how they react to a situation, how to grab that data, and why they're grabbing it to get that analysis. The fact that the software may or may not record the data and or make a graph for them is irrelevant because then you can have them use those graphing tools to do a more complex analysis because the data is already there for them. Availability of program materials for students. Again, making it available, because if the software or the site is not working, it's no different than having the equipment break down in the lab. And adaptability to current approved curricula. Again, not only vital, but extremely crucial when it comes to redesigning your curriculum. I've taken most of my labs, and the only thing that I would have to do is change the procedure to match the software. I should never have to change my analysis for a virtual lab. Thank you very much. My contact information is below should you have any questions. Again, thank you.